Hello, Internet, and welcome to my longship. So, I was recently inspired by Splitsie's Wrong Way Out series to mess around a bit with their sort of primary challenge, which is that they cannot build control seats on large grid. So, any controls have to be done either through buttons or, using event controllers and levers and stuff. They have to get weird. And I like weird. And thinking about weird control methods, I thought, what would make a lot of sense would be a sort of tiller lever off like, an old rowboat or, smaller sailing boat or maybe a Viking longship. So, as you can see here at the back of my glorious land vessel, I have a tiller for controlling left and right, and then I have a little throttle lever for forwards and back. And the star of the show is this strange blue device down here. This is my blinking light Controlomatic, which is essentially, partially it's just a small grid way to have all the event controllers I need to control stuff, but it's also doing some slightly complex computation in order to make this whole vehicle drive like this. So we're moving forward, as you can see. If I push my tiller, we start yawing left. Then I want to start going straight again. Push my tiller back. The wheels automatically kick back into forward and I'm moving forward again. This took much more thought and fiddling than I really anticipated when I started doing this, but we made it. So today I'm going to show you how. I'm going to first just talk a little more on why I chose, this as a vehicle. And it's mainly, so I had the tiller idea, which was, I want some sort of like old sailing boat where you'd have the lever at the back, because then you have a lever to push back and forth. And I was thinking, well, what old-time boat also has round things on the side? Well, that would be a Viking longship with its shields. So, I have these shield wheels, which are maybe a little oversized. They have created some challenges in and of themselves because I wanted them to be at the right height for the shields, which is like at the, there's a term for this part of the boat, but I can't remember it. At this part. Which meant ground clearance was a little tight. So I've had to lop the bottom just a bit. I could have even gone lower with panels, but I didn't think about that until I'd already built all the stuff inside it. Surprisingly though, even with this ground clearance and, protruding prow, it does do a decent job of moving over relatively, acceptable terrain. You can note too, I have converted from large grid to small grid for the wheels just to make it a little more compact and manageable. And while we're at the wheels, I guess I should talk a bit about their design because there are some things to note. So because I wanted to use small grid, I needed big enough wheels to give myself clearance for, the height issues. So I used the 2x2 or 5x5. I used the big ol' wheels. And the interesting thing with the big ol' wheels is because they're 4 blocks, they're pretty much entirely offset. So the middle of the wheel, like when the wheel is normal, it would be way down here. Which, actually looking at now, had I just built it on this block instead of this block, that would have solved that problem. I didn't think about that, so I built them the stupid way and then adjusted the height offset so that the wheel itself was in the middle of the axle. So all the wheels are lined up. You can see I have this small rotor connecting to those. I could beef that up a bit more, but I don't need to. They work pretty well, this sort of dual system design. They pretty much behave just as wheels would. That part's more or less, you can do whatever you want with all that. The real interesting part is this machine. So this took a lot of iteration and fiddling to try and figure out what I needed, how to, all the steps I had to do. And I came down to this machine, which has on it a grid of 9 event controllers along the back. I have 5 timer blocks, and then there are 4 lights. So you may be wondering, you have event controllers, timer blocks. What are the lights for on this strange machine? Why are some on, some off, one blinking? The blinking's just for style. The way I've set this up is I have event controllers turning the lights on and off, and then another event controller watching those lights, and that is what controls my movement. So essentially, the issue I ran into was that when you have an event controller and you use the AND gate, you still only have one event to control. So let's look at, this one has some more info. So if you imagine there were 2 things here, and I had the AND gate selected, so I'm watching both blocks, I can still only compare if both of them are equal or greater than 15 degrees. So for a situation like I have, where I have multiple inputs at once that are different, I couldn't compare them in enough detail to actually do anything. So say I'm in forward gear and I want to turn right. Well, this hinge is positive. If this rotor is negative, I don't have any way to control that. So essentially, the lights are serving as a sort of memory buffer, if you will. The light tells the system what state one of the controls is in while I move the other, and it does it in such a way that those states can always be compared to one another. I should probably warn that this is going to be a rather technical tutorial, and I'm probably going to do a poor job of explaining it, because I only barely muddled through it, so yeah. Anyway, let's dive into what's actually going on here. So, to start off, we have our timer blocks. So these timer blocks control all the various movements. So my forward timer block, if I look at its actions, it sets the left and right rotor groups to spin in the correct direction for moving forward. It also turns those rotors on, which is important for how I manage the turning. Reverse is the same way. Stop does essentially the same thing, except this is setting them to 0 instead of a velocity. I guess 0 is a velocity. But that essentially works as a brake. So for turning, what I do is I have my left and right rotors in 2 separate groups. So left rotors and right rotors. To turn, I turn whatever side I want to turn towards off. I've set the rotors up with decently high braking torque. And this was sort of something I fine-tuned so that as we're moving forward, if I turn, we pull to one side because those rotors have more resistance, but we are still sort of moving forward. I actually upped it a little bit, which maybe, was or wasn't necessary. It depends on how you want this thing to control. Upping the resistance means tighter turning. Lowering it means you're moving forward more while you turn. Theoretically, you could have that controlled separately and adjusted as needed. And because my turning timers turn off part of the rotor group, that's why I have the other timers turn everything back on, just to make sure everything is on correctly to reset. Now these timer blocks need a system to trigger them. My triggering is done with my bank of 9 event controllers. So these event controllers are sort of broken up into 2 groups. You have event controllers controlling lights, and then event controllers that control actual motion. So this event controller forward light, it is what's watching my throttle position. So when I push that throttle lever forward, it moves that. And what it does is turn on the forward light and turn off the neutral light. Then when it's no longer above 15 degrees, it reverses that, turns on neutral, turns off forward. So I have these lights to track the state of the hinges, and the primary state I need to check is the throttle, because the only thing I'm worried about is returning to whatever motion I was in when I finished turning. So, we have a forward light, neutral light, and reverse light. The forward light is on when the throttle's in forward. The neutral light is on when the throttle is in the middle, so neither forward or reverse. Then reverse, of course, is when it's in reverse. The reason I have these three lights is because I have a throttle with three potential states, and event controllers are binary. You can only check if a state has occurred, which is part of why I need the lights in the first place. They're essentially converting that trinary input, I don't know if that's the right term, into a binary input that can be checked and compared with the only Boolean we have, which is an and a very limited and. So the lights essentially record whatever the throttle is, and that really comes into play with these two event controllers. So, I have a straight forward and straight reverse. The other light we have, the one that is blinking yellow, is our straight light. That is turned on whenever left or right is not true. So whenever the tiller is dead center. So my left and right event controllers actually are working differently to the forward, neutral, reverse, because I don't need as much information. I don't really care if we've turned left or right, I only care when it's returned to the middle. So, these controllers directly watch the steering rotor, which is what the tiller's connected to. When they're triggered, they trigger the timer block for their respective turning side, which turns off those wheels, and they turn off the straight light. When the state is no longer true, it turns on the straight light. And that is what tells the event controller system we are no longer turning, we are now going whatever direction we were originally going in again. The straight forward and straight reverse lights watch both the straight light and whatever their respective direction is. So straight forward is watching for the forward light and the straight light. It's using the AND gate, and if both those lights are on, it triggers forward. Now, an interesting thing with event controllers and how they sort of work, because they detect a change, they can't be passively checking a state. That's part of why I need a neutral light and a straight light. Well, I think a straight light would be required regardless. But the neutral light is there because something needs to turn on to trigger the stop event controller when the thing is no longer in forward or back. So the general idea to remember is that you need something to change in order for any event to occur. So, even if theoretically you only care about forward or reverse, you need something neutral just so that you know a change has occurred. It doesn't necessarily always detect that a state has stopped being a thing. So let's just go through a general sequence of how an event will go through the system. That may explain this a little better as a different way to look at it. So, the first thing I would do is push my throttle forward. That gets detected by this forward light event controller. This forward light event controller then turns on the forward light, turns off the neutral light, which means this forward event controller, which is watching the forward light, sees the light turn on and then triggers our forward action. So now that we're moving forward, I decide I want to turn left. So I push on the tiller in the direction that will tell the ship to turn left, which is pushing it right, and it activates this event controller, which is watching that hinge or rotor. The left event controller then triggers left, turning off the left side wheels, turns off the straight light. So now we're turning left because the forward state is applied only to the right side wheels. Now I'm done turning left, and I decide to go straight again. Well, when I push the tiller back into the middle position, this left event controller is no longer applied, which triggers the second state, which turns the straight light back on. When the straight light turns on, it triggers one of these two event controllers, our forward in this case. So the forward light has stayed on this entire time because the throttle has not moved. And the straight light just kicked on, which the change triggers this timer block to check the state of both of these. Because of the AND gate, it's checking if both of these lights are turned on. Because they both are, the system knows that we were in forward gear and we are now moving straight again, so it re-triggers the forward timer block to reset all the wheels to move forward and turn on. So that is the gist of how this machine works. It's surprisingly complex for what is not all that complex of an idea, just returning to the previous state you had. But space engineers, this is the way we are given to do it. In reality, this is essentially physical programming. I have lights that turn on during a state, they save the info on that state, and then essentially tell a basic logic circuit what to do. So, I suppose, now that we've gone through the gist, let's see if we can climb this hill. And actually, because I think I've only ever showed forward, I can go in reverse, and I can turn in reverse. So that all works. Theoretically, if you didn't want this to be set up like a boat, this could be the front, and it actually makes a bit of sense steering-wise. Oh, I think that's an old... Yeah, I didn't realize I was so close to that. A previous thing I was testing. Yeah, all in all, this whole sort of... The idea of physical controls is kind of cool. Because it does make the whole world feel a little more, immersive, a little more real. You actually have to physically move a thing. And I should note, too, I'm doing this whole vehicle is set up to work without the, what a grabby hands mod that lets you manipulate stuff. So I'm physically just pushing into bars. Which is cool. This is fully vanilla. You could do this without any sort of, mod help. It's not quite as easy, but it's cool that this weird way of playing the game just works. Alright, do we hit things? No. We're pretty close. And it's just climbing right up, no issue. An interesting thing with this system, I don't know exactly how much you would need. I'm guessing you would need at least one more light, maybe 2 event controllers for any, extra speed steps. It does become, I guess, exponentially more difficult. Just turn around these trees. Yeah, it does become exponentially more complex, God, of a ship to, or of a system to design as you add, like, say I wanted a turn gently and turn hard, or I wanted different degrees of forward. You could do it, it's just a lot more sort of setup effort. Pretty much any way you do this, you would need that setup effort. And I will say, at least control-wise, this could really make some sense. Especially because you could imagine, you know, say instead of the antenna up there, you had a little crow's nest. So you could have someone up there, like... I should dampen to this very slow-moving thing. Yeah, you could have someone standing up here, guiding where the ship needs to go, while someone else down below is doing the actual steering, which is very fun. Yeah, I think this, as convoluted and complex a machine as it ends up being, it really does make this work, and I could be wrong. Feel free to experiment yourselves and see if there's a better way to, you know, further optimize this sort of system. But I think this is pretty much, like, this thing is probably as compact as you could get it and still have something that works reliably for all the states that you need for sort of normally expected vehicle movement. Now, I am curious, because this is a fairly light hill. Let's see if this thing can manage up this big hill. Which actually doesn't look too big. Alright. Third hill time. That looks big enough. Yeah, I think this should be a decent test. And I should note, I do not expect this thing to be this capable. I mean, for one hand, it's not very well designed for slopes. It's got very poor ground clearance. But the impressive thing with this style of vehicle is they just keep going. Rotors essentially have sort of unlimited torque, or at least way more torque than you'd ever want out of a wheel. So it may just keep climbing, assuming I don't slip or fall over or, you know, rip the middle of the boat out. Or hit one of those trees and just stop. I don't really have the momentum to deal with them. Let's see if we can get to the top of this. Alright, we are steeper than any Viking longship has gone before. At least it wasn't sinking, I guess. We definitely no longer turn... Oh. Uh-oh. We no longer turn in general. Oh no. Oh no! Okay, that's an interesting conundrum. Because of the angle, I'm now walking onto the tiller instead of controlling it. I can't turn left. Oh, good. Okay. Well, this hasn't gone quite correctly. This is something where grabby hands may help. Can I turn left back up the slope? Oh, no, because I'm turning right. And I can't... Uh-oh. Okay, well... I've gone back down. I guess I could loop up and try again. I think it's partially because not all of the wheels were fully on the ground. But turning did become tricky. Also gonna... That's not what I wanted. Oh, that's also not what I wanted. Alright, take two. Let's go ahead. try and turn around this tree. Then I'm just gonna charge straight up. Now, what I was saying before I cut my tiller in half, I think that part of... That's good enough. I think part of my challenge with turning on the slope was that not all my wheels were on the ground, which meant they had less friction. Or I guess less resistance, because there was one less rotor providing that resistance. So that is an interesting drawback of the design. Let's see. Yep. I'm very surgical with my removals while moving. Hopefully this wider paddle will help me steer better. Well, we do seem to be going upward. Okay, we're turning, so let's turn that way. Oh, I think we just... Oh, wheels. Uh-oh. Okay. So downside of this... Oh. Okay, my throttle fell backwards. That illustrates it. A downside of this, because I'm at such a strong angle, there's braking torque on the rotor and hinge that mean they stay put, but that braking torque can be exceeded because I need to exceed it. So I think part of my issue with control is that, yeah, my controls keep moving because of gravity. So that's not something you'd get with a control seat. We're definitely going up still. I can stand back here on the 45-degree slope and be flat. Yeah, and look, we're going over crags. Oh, okay. Well, the throttle stays in position. We're going over crags without issue. Maybe. We might just be bouncing up and down on crags. Oh, nope. Throttle, go. Oh, God. Open, my tiller's rotated. Okay. Oh, God. Okay, we may be encountering the limits of this vehicle. This... Oh my God, I'm having to constantly adjust the controls to move. Okay. Come on. We are going almost vertical. Oh, okay, we're taking some damage. The hinge is broken. I don't know if that matters. Oh boy. We're still turning somewhat. Okay. Oh, a wheel's off. We're still trying to move. I think I still have steering. No, I can no longer turn the tiller the other way. And we're in a tree. Okay. Well, I think that's where we'll call this. We almost made it. It just, yeah, this part it didn't like. But that's fine, I suppose. We very nearly bisected it. Yeah, so, that's how this was built. I'll, publish this vehicle to the workshop for anyone who wants to mess around with it and, you know, get a hands-on view as opposed to my mad ramblings. But yeah, thank you everybody so much for watching. I hope it inspires you to do some of your own weird, wacky engineering. Until next week, bye-bye.